In our recent videos, I introduced the VSEPR model, valence shell electron pair repulsion model, and our goal was to get from Lewis structure to intermolecular forces. And really to do that, the VSEPR model is all that we really need because the shape and then being able to figure out symmetry is sufficient to be able to do that. So in this video, we're going to take a little bit of a detour for just a moment. This is not critical to answer our IMF stuff, but it's important to understand, at least be familiarized with it. So what I want to talk about is valence bond theory. This is a theory of bonding that came along after VSEPR, and what it did was attempt to describe those domains. Like, what are they? How are they forming? What do they look like? What are some properties of these domains and these bonds that we're seeing formed according to the VSEPR model? So let me begin this by going through an illustration, and I'm going to use methane as my model molecule. So let me explain what you see on the screen now. We are drawing or using methane to discuss the concept of hybridization as part of valence bond theory. Now, across the top, I've drawn you the orbital notation for carbon. Carbon has 4 valence electrons. I've used helium for the inner core because I'm not worried about those 1s electrons. I'm looking at just the valence shell. And let me briefly explain that normally we would have drawn carbon as 2s up down and then 2ps up, 2py up, and then there will be nothing in the z's. But we have learned that when central atoms prepare to bond, part of this theory is that we decouple the electrons that are paired up and promote them to other orbitals in order to spread them out. So all I've done here is, following valence bond theory, I've taken the down electron that was in the 2s and I've moved it to the 2pz here. So I've separated all 4 of carbon's valence electrons now into their own orbital. Now here I just briefly did the orbital notation of hydrogen just to remind you of what it was, and then I've drawn that 4 different times over here. Finally, on the bottom left hand of the screen, you see the Lewis structure for methane. There are 4 individual carbon-hydrogen bonds here. And let me begin this by posing you a question. Do you think those 4 bonds in methane, the 4 CH bonds, are all the same, or are they different? Logically, many of you think that they are all the same. But let's take a closer look at how the bonding actually occurs. We know that every one of these carbon-hydrogen bonds is the overlap, the sharing of electrons between a hydrogen and a carbon. So let me illustrate that over here by circling that. Now that illustrates one hydrogen overlapping with the 2s orbital of a carbon to form one of these bonds. So let's call that 1 and we'll label that 1 here. Well, let's do it again. So here I have another overlap with a hydrogen and a carbon. Let's call that 2, and we'll just go clockwise. And let's do it a couple more times. We can overlap the 3rd and 4th time. And I'll ask you again, are those 4 bonds in the methane molecule the same, or are they different? Well, maybe you're still not sure. Let's look at what actually had to happen over here in our overlaps. On the very end here, I had a PS overlap, an overlap of the P from the carbon and an S from the hydrogen. Okay, well, no big deal. The next one, at number 3, was also a PS overlap. It doesn't matter that it's PZ or PY. Remember, the P's are all the same, it's just how they're oriented, along which axis are those P orbitals pointing. So a PS overlap is the same no matter which P it is. And we have another one here with a P and an S. So far things are looking pretty good. But now, what about this first one? I have a 1s of hydrogen overlapping with a 2s of carbon. This is an SS overlap. We've learned in quantum numbers, when we learned about orbitals, that s and p orbitals are slightly different. They're different energies, they're different shapes. So now would you expect the 4 bonds in methane to be the same? Now you're probably leaning toward the answer being no. Well, that's incorrect. They are actually the same. We have instrumentation that allows us to go in and measure the bond angles, and we can calculate the bond energies in any molecule. And it turns out that each of the 4 bonds in methane end up being all the same. Same energies, same distances, all of it. So now we have a conundrum. Obviously, from looking at the overlaps, one of these bonds should be different. But empirically from the lab, we have proven that they are all the same. So now, if you're a scientist, you want to answer the question, how is this possible? And that's where hybridization comes in. Hybridization is an attempt to try to explain what happens from the overlap of these different orbitals to end up giving us the same type of bonds. Let's talk about the process of hybridization. Like, what does it mean to make a hybrid? This is kind of the same idea nature finds itself in from time to time. If a horse and a donkey mate, you get a hybrid animal, which has properties of both the horse and the donkey. We call it a mule. The same thing with lions and tigers. We make ligers and tigons. They have the properties of both of the individual parents. We're going to do the same thing here with orbitals. If I take an s orbital and I blend it with a p orbital, mix them together, just like when you were kids, you take red Play-Doh and green Play-Doh, you smash them together and you blend it together. That's what we're doing here. We're smashing them and blending them. When we do that, we make what are called hybrid orbitals. So take a look at this, and you can see that when I mix an S and a PX, I make this hybrid thing that looks a little bit like a piece of both. And we call that an SP hybrid. Okay? And so the SP hybrid is just a mixing. You get something out that's equivalent. Okay? So that's what we mean when we say hybridization. So how does this affect our methane example? Well, from the Lewis structure, we can see that there are 4 domains here. We took all 4 of the orbitals for carbon, and we did a little pre-mixing. This hybridization process actually happens before the hydrogen atoms come in and overlap. So this is a pre-bonding process. In this picture, you can see what kind of happens. I take an S from the carbon and the 3 P's from the carbon, and we're going to smash those things together, all 4, like Play-Doh when we were kids. Mix it all up, and then I'm going to divide it back out evenly. If 4 things go in, 4 new things come out. So an S, a P, a P, a P, that's 4 orbitals. I'm going to get 4 hybrids out. Okay, whatever you put in, you get out. And look at the picture here. You can see the shapes of these new hybrid orbitals. They bear parts of the S and P properties. Now, when you put all those pieces back together, look what you actually make. We still get that tetrahedron geometry that we learned about from the VSEPR theory. So this is how VSEPR and valence bond theory sort of work hand in hand. What about if we have an example where we don't need all of the orbitals? What if we don't need the PZ orbital, for example? That happens. So in this illustration, we have a 2s, a 2px, and a 2py that need to bond. So because maybe we only have three terminal atoms to work with. So the 2pz is unneeded. So we will only hybridize what we need for bonding. And then in this case, we put 3 in, we get 3 out, and they're called sp2 hybrids. S and then 2 p's, not 3 p's. And the pz remains unchanged. It's called an unhybridized orbital. And that's very important for bonding theory, because those unhybridized orbitals still contain, or potentially contain, an electron that's available for bonding. And those electrons in the unhybridized orbitals are going to do something very special. They're going to be the ones responsible for your multiple bonds. So this goes a little bit into sigma pi. I'm not going to really do sigma pi in this video. This particular slide, I want you to just notice one thing. In this picture here, we have 1, 2, 3 hybrid orbitals. Those are sp2 hybrids. And the blue one here represents an unhybridized pz orbital. So you can see in this particular case, as we're making a bond here, we have some overlap to make us what's called a sigma bond. And those unhybridized p orbitals are just kind of sitting there. Well, eventually what's going to happen is that as the carbon atoms in this example are drawn closer together through this bond formation, these unhybridized p's are going to get really close together. They're going to get so close that they can actually start, you're going to see some blurring of the borders. It's kind of like when you paint. If those of you who've ever painted with watercolors as a kid, if the colors get too close, they start bleeding into each other. That's kind of what happens here. And eventually they just kind of lay down and go into the new plane to form a multiple bond. So here they're perpendicular to the plane of bonding, so we have trigonal planar. Well, I should back that up a little bit. So when they're perpendicular, we kind of have tetrahedral geometry, and it would be trigonal bipyramidal. But when they lay down and bleed next to each other, they lay down into the current plane, and the geometry turns into trigonal planar. And that's very important. That's why multiple bonds only count as one domain when we count up our electron domains. They come from unhybridized p orbitals that eventually lay down into the plane. So that's hybridization. Understanding it, at least superficially, is really kind of all you need to do. But let me go through and just show you how you can use your fingers to count and come up with a hybridization scheme. Before I do that, let me remind you again real quickly that every electron domain, or I should say each electron domain geometry that I taught you, has its own hybridization scheme. So if you're linear, you only have 2 domains. If you're trigonal planar, you have 3. Tetrahedral, you have 4, and so forth. So let's let these each represent one of our electron domains. Linear, trigonal planar, 4 is tetrahedral, 5 is going to be trigonal, bipyramidal. It's pretty neat writing there. And then we have octahedral. Okay, so those are our 5 domains. Here's how you can use your hand to count. If I'm linear, I have 2 domains. I'm going to need 2 orbitals. I'm going to need an S and a P. All right, so that's 2 fingers. And what does that mean? You're going to get 2 sp hybrid. The number of fingers you have up tells you how many of those orbitals you're going to have. You have 2 sp hybrids. If we go to trigonal planar, you need 3 domains, you know that. So you use your fingers, you count an S, you can count a P, let's call it a PX, and you can count a PY. So you have 3 fingers in the air. That means you're going to have 3 hybrid orbitals. Okay, but it's not sp because there are 2 p's. This is going to be sp2. So you're going to make 3 sp2 hybrids. 3 fingers in the air, 3 orbitals, you get 3 hybrids. Tetrahedral, you're going to have 4 fingers in the air now. So if you need 4 domains, you're going to use an s orbital, a px, a py, and a pz. Okay, so you got 4 fingers in the air. That means you're going to make 4 hybrids. And those hybrids are going to be not SP, not SP2, but I have 3 P's in the air. So these are going to be SP3 hybrids. All right, I hope you get that point, because I'm not going to write out all 5 and then all 6 in the last 2 examples. For the expanded octets, I need 5 domains. So I'm going to need a S, a PX, a PY, a PZ. And now for the 5th one, I want to go into the d orbitals. So let's just say we're going to use a dz squared. I think that's one of the ones that comes out first. It's irrelevant, okay? Don't worry about it, just AD. So I have 5 fingers in the air. I'm going to make 5 hybrid orbitals. That will be S. I have 3 P's in the air, and then I have 1 D. So it's sp3d hybrid. 5 fingers, sppd, sp3d. And then finally, for the octahedral, we're going to need an S, we're going to need a px, we're going to need a py, we're going to need a pz, maybe the same dz squared, and then maybe dx squared minus y squared. Again, it doesn't matter which d's, just conceptually we need these. I have 6 fingers in the air, so I'm going to make 6 hybrid orbitals. I've got 3 p fingers in the air, and I have 2 d fingers. So sp3d2. The sum of your quote-unquote exponents here should add up to the number of fingers you have in the air. So for sp3d2, that's 1 s, 3 p's, 2 d's, that's 6 total. I have 6 fingers in the air. So if all you need to know is which hybridization scheme you are in, you can easily count this on your fingers. Again, this is not going to help us do IMFs or anything. It's just showing that you understand that some things have to happen behind the scenes to make bonding theories work out. Otherwise, when we draw the Lewis structures and look at the different domains, we would see different domains, and that is not what actually happens. All right, I think I have some supplemental videos that will attach with this. If you have any questions about anything you saw here or those supplemental videos, hybridization is kind of out there, so if you just want to talk about it, come by and see me and we'll work through it.